Okay, guys, welcome. This is section 9.2. We're going to start talking about parametrics today. We're just going to do about half of chapter 9. We're going to get the basics of parametric equations and polar equations, and starting with parametrics today. And basically what a parametric set of equations is taking x and y and looking at them separately. Just focusing on what x is doing as time passes, or just separately focusing on what y is doing as time passes. Imagine that, you don't need to draw this, but let's say, stuff that's flying through the air travels in a parabolic shape. So let's say this is a golf ball that's been hit. My illustration of parametric would be kind of like when you look at it from the blimp's perspective. The Goodyear blimp films golf shots from above. If you're looking straight down on this, you really can't tell how high the ball is. I know when you're spending your Sunday afternoons watching golf coverage and you see that blimp shot, all you see is the white speck moving across the ground. You can't tell that that ball is getting closer to you and then further away because you only have one point of view. If, let's say, you're up by the hole and you're standing here watching this way, all you can see is the ball going up and then coming back down. And you know in your mind that it's coming at you, but you really can't see that because from your point of view, if this is the back of your head and little golfer guy is way back here and golfer guy hits the ball, you see the ball go up and you see the ball come back down, and you kind of only see the y direction. The blimp kind of only sees the x direction. That's kind of a rough example, but that sort of sums up what it means to only look at one direction at a time. You just concern yourself with the horizontal movement or just with the vertical movement. So back to the math side of it. To graph a parametric equation, kind of think of t as time. We use t because anytime a word problem comes up, that third variable that x and y are defined in terms of will probably be time. And this is an example of a set of two parametric equations. X is t minus 1 and y is t over t minus 1. So basically as time ticks away, in time it might be start at negative infinity and go all the way up to positive infinity. Sometimes certain t's will be undefined. We don't know. So I just picked a few left of 0 and a few right of 0 just to see what we get. So for instance, I'm going to start by plugging in my first t value into x, and I'm also going to plug it into y, wherever I happen to have a t. So if t is negative 3, then my first x value is negative 3 minus 1, which is negative 4. If t is negative 3, then my y value is negative 3 over negative 4, or 3/4. All right? So you still graph the x and y just like normal. It's just that we specified this is at a t value of negative 3. So negative 4 3/4 is the first spot on my graph. It's about right there. Once you've determined the xy points, it's graphing just like you've always graphed. All right, negative 2, when I plug in negative 2 for x, I get negative 2 minus 1, or negative 3. And when I plug it in for y, I get negative 2 over negative 3, or 2/3. So negative 2 gives me negative 3 2/3. So there's negative 3, there's 2/3, just a slight bit lower than 3/4 was. All right, so I think you get the idea. You plug in the t's, each t creates an xy point, and you connect dots. I'm going to pause and fill these in so we don't take up too much time with this stuff. Okay, so I've filled in the rest of the x's and y's that go with those t's. A couple of interesting things. When I try to let t equal 1, my x is 0, but my y is undefined. And you can kind of see what your graph was doing. It was coming in from a horizontal asymptote, approaching this vertical asymptote, like that. And then it resumes up here, the vertical asymptote, and comes on down this way, and the horizontal asymptote is at 1. All right, and my undefined there on that y, when t was equal to 1 and x was 0 and y was undefined, it was because I had 1 over 0, which is infinity or negative infinity, and that's where the horizontal or the vertical asymptote came from. It also happens to have a horizontal here. We're not really worried about what made that happen. It's just what happened. Now, graphing a parametric is that easy, other than one little thing. You need to indicate which direction this thing is going. If t were really time, we need to let time go forward, because smaller t's progress towards larger t's. So my first dots that I made you just need to put a little arrow indicating that this is the direction that your graph is going, because there's a difference between arrows going that way and arrows going the other way. So that's kind of just a technicality, but you need to do that. So whichever, this graph could have just as easily been moving the other way, and I would have put arrowheads going that way and that way, but it wasn't. It was going the way that's indicated. So other than that, the graphs are pretty similar. I want to show you in your calculator. If you go to mode in your calculator, my version, the fourth line down, has a whole option for parametric. So if you turn that to parametric, this makes some changes in your calculator. When you go to graph something, now you have x of t and y of t. So you can already see that it's going to change a lot in your calc. If you've ever wondered why your x button has an x, t, theta, and an n on it, this is why, because parametric uses t instead of x. All right, so if you type that in and then go to graph it, you can see the graph that we just made. All right, these two graphs are the same thing. All right, next, you can convert between normal, or what's called a rectangular equation, just a good old-fashioned xy equation, and parametric equations. So I'm going to take the two equations that I had in parametric form and turn them back into a regular equation. All right, and this is going to be done just through a substitution. And if it's t we're trying to eliminate, this is called eliminating the parameter, by the way. T is called a parameter, that's the name parametric. If you're trying to eliminate t, then solve one of your equations for t, and then sub into the other one. So if I take this equation on the left and figure out that t equals x plus 1, then in my other equation, I've got x plus 1 on the top, and I've got x plus 1 minus 1 on the bottom, which just leaves me with x plus 1 over x. And, we could analyze that graph. It's also 1 plus 1 over x. And, you've been able to graph something like that by plotting points or talking about asymptotes. You've been able to do that forever. So just a quick check on my calculator, x plus 1 over x. If I change my mode back to function, which is just regular, and then I go to graph, and get rid of my old graphs. If I want to graph x plus 1 over x, notice how my x button is now producing x's again. And I go to graph that, I'm going to see the exact same graph. So parametric is just another way to do the same graphs. And why have another way? Because sometimes in different applications you want to just look at x or just look at y. And this allows us to do that. The only difference in the two graphs is that one needs directional arrows on it and the other one does not. Okay, so that's going to be our intro to parametrics. You need to be able to graph one by plotting points and just charting what t gives you what x, y. And then you need to be able to eliminate the parameter through substitution. So nothing too bad yet. Next time we'll start talking about calculus and derivatives and stuff with these. But for now, let's just call that the intro to parametrics. All right, so I will see you next time in class. If you have a good one, Young out.